Hello there, my name is David Wangal, and today I'm going to be presenting a paper discussion on this paper, SegNeXt, Rethinking Convolutional Attention Design for Semantic Segmentation, published at NeurEPS in 2022. Here are the authors and their affiliations, just for reference, and now let's get into the paper itself. So the main contribution of this paper is a novel deep neural network architecture designed specifically for semantic segmentation. And of note is that the authors replaced the expensive self-attention operation with cheaper convolution operations. And they find that their new architecture achieves state-of-the-art results for semantic segmentation, achieving better results over both older convolution-based methods as well as contemporary transformer-based methods. So here's how the authors frame their contribution. They frame it as combining properties of networks that lead to strong semantic segmentation results. So let's walk through them now. So first, they argue that a lot of progress made by transformer-based methods is due to vision transformers just plainly being a stronger encoder than the older convolution-based encoders. Secondly, they argue that the new transformer-based methods don't have as much multi-scale interaction as the older convolution-based methods. They also note that transformer-based methods have this advantage, that advantage being the ability to achieve spatial attention via the use of self-attention, which is applied over different patches of regions of the input. However, self-attention is an O of n squared operation, which is one of its main drawbacks. But the authors claim that their SegNeXt architecture achieves all of the benefits that are listed here with only an O of n computational complexity. And we're going to see how they do this. So, SegNeXt is an encoder-decoder model, which follows the convention of many other successful semantic segmentation architectures. So input is sent into the encoder, the output of the encoder is sent to the decoder, and then the output of the decoder is used to predict the final semantic segmentation mask for the given input image. Let's start by taking a look at the encoder. The encoder is called the Multi-Scale Convolutional Attention Network, or MSCAN. So MSCAN is comprised of 4 stages. So input comes in, and a patch embedding is applied. Then it's processed by the MSCAN stage. Then the output of that stage is sent to the next patch embedding before being processed by the next stage, and so on. And we store the output of each stage for later use in the decoder. Notice that the outputs are spatially scaled down by 2 at each stage. The H and W here refer to the height and width of the original input image, and the E1, E2, E3, and E4 are the embedding dimensions for each stage. Just for reference, let's quickly take a look at what happens with the saved outputs of each stage. So the output of stage 1 is discarded, while the outputs of stages 2, 3, and 4 are sent to the decoder. Now we're going to come back to how and why we do this, and what happens in the decoder itself. But for now, let's dig further into what happens in each MSCAN stage. So here is what is inside each MSCAN stage. The block with the name BN is a batch normalization layer, which we should be familiar with. And the arrow that skips over the blocks is a residual connection, which should also be familiar to us. So now let's talk about the first unfamiliar thing, which is this attention block. Here are the layers that make up the attention block: a pointwise convolution, a GELU activation, the multi-scale convolutional attention module, and one more pointwise convolution. Again, let's look at the piece that's unfamiliar to us, which is the multi-scale convolutional attention module. Here's what it looks like. So there are a couple moving parts here, so let's talk about each one. First, there is a 5x5 depth-wise convolution. The 5x5 kernel is used to capture more local information and local relationships, as opposed to the larger kernel sizes that we're going to see further down the pipeline. So then, the output of the depth-wise 5x5 convolution is passed into 3 separate branches of what are called depth-wise strip convolutions. So these are a decomposition of a k by k convolution into a 1 by k convolution, followed by a k by 1 convolution, to save on computation. Now you'll notice that we are using particularly large kernel sizes here. Now why would we want to do that? Well, consider that the self-attention mechanism used in transformer-based methods is used to model these long-range relationships in an input, i.e. regions that are far away from each other. So the idea is that if you use a sufficiently large kernel size for a 2D convolution, you can also model these long-range relationships because more area of the input is going to fall within your kernel. Now, the use of large kernels in convolution is typically very expensive, and that's why they use these strip convolutions. And the strip convolutions are applied at a few different kernel sizes to model these relationships at multiple scales. This is the multi-scale interaction that was talked about near the beginning of the presentation. So after that, we take the output of the depthwise 5x5 convolution and the output of each strip convolution branch and sum those four tensors together element-wise. Now I should note that when these convolution operations were applied, there was strategic padding and striding used to ensure that each output is of the same dimensionality when we get to this summing stage, so that we can actually perform this element-wise addition. So after that, a pointwise convolution is used to unify channel information. This is sort of like the depthwise separable convolution operation. The depthwise convolution operation applies a unique kernel to each channel, and so the pointwise convolution is used to perform a linear combination of the responses in each channel, so that they have some sort of interaction. So the output of that pointwise convolution is the attention map, which is then element-wise multiplied with the input to the module. We can think of this map as a weighting of what is important in the input of the module. And this importance was generated by looking at the input at multiple scales, ranging from very local to more global. So that was the attention block. Let's now move on to the feed-forward network block. This block is more straightforward. It's comprised of a pointwise convolution, a depthwise 3x3 convolution, a GELU activation, and one last pointwise convolution. This block is called the feed-forward network block, but instead of using a fully connected layer like in a plain multi-layer perceptron, they reinterpret those as pointwise convolutions. Then, this set of operations is repeated L number of times, and we're going to see on the next slide how L changes throughout the different stages, and how that change will differ between different sizes of SegNeXt architectures. So, here are the four SegNeXt sizes that the authors present. We see that the way the L parameter changes is different among each of them, as well as for the embedding dimensions and the decoder dimension. We see that the expansion ratio, that's the ER in the third column, is consistent across the different sizes. Someone asked me this when we gave the presentation initially, so I'm going to give a little more clarification. The expansion ratio is the factor by which the embedding dimension is expanded during the feed-forward layer before being returned to its original size. So for example, at stage 1, the embedding dimension is expanded to 32 times ER times 8, which is 256, and that's done with the first pointwise convolution. And then it's returned back to 32 by the last pointwise convolution. So that was the MScan encoder. The authors ran some experiments using the encoder as a classification model and benchmarked it on the popular ImageNet dataset. The authors show that against models of similar parameter size, each of the SegNeXt models achieves better top 1 accuracy. Now obviously, this is not a comprehensive comparison, so please take these results with a grain of salt. So now we have the outputs from the 4 MScan stages. As I mentioned before, the outputs from stage 1 are discarded. This is because the authors found that they could achieve good results without including the stage 1 output. Their theory is that the features in stage 1 are just too low level to be useful to the decoder, compared to the potentially more complex representations at later stages. The next step is upscaling the outputs of stages 3 and 4 to be of the same dimensionality as stage 2. That upscaling is performed so that these tensors can all be concatenated together. And this set of concatenated tensors is the input to the decoder. So let's now talk about what takes place in the decoder. First, a pointwise convolution is applied to get a linear combination of the features from the various stages that are used here. Then the output of that is passed into a Hamburger module. Then another pointwise convolution is applied. Finally, there is one last pointwise convolution applied that results in a tensor with the number of channels being equal to the number of classes in the dataset that the model is being trained on. Now at each pixel location, we have the logits for the pixel-wise classification. By using an argmax operation, we can denote the predicted class at each pixel. and that is the SegNeXt architecture. So you may have noticed that I very quickly glossed over the Hamburger module in the decoder. That is in part because the SegNeXt authors also gloss over it in the paper. The Hamburger module comes from this paper, Is Attention Better Than Matrix Decomposition? Something of note is that the second author on the paper that introduces the Hamburger module, this paper, is also the first author of the SegNeXt paper. And I think that sort of helps to explain why it was mentioned very nonchalantly in the SegNeXt paper. So what exactly is the Hamburger module? So it asks, what if we interpreted the issue of modeling global context as a low-rank recovery problem, instead of using self-attention to achieve that global context? I think this is a wildly fascinating concept, but I have just not been able to completely digest this paper yet. That being said, I think it would be interesting for us to take a look at this paper in the lab, and maybe it can turn into a paper discussion presentation later on, by myself or someone else. In any case, let's talk about some of SegNeXt's results. So here we have the ISED dataset, which is a benchmark dataset for semantically segmenting certain classes in satellite imagery, which is the result that the authors showcase, which I think is the most relevant to our lab. We see that the SegNeXt models are achieving higher scores than any of the other models presented here. Again, though, with this slide and the later slide where I show some other results on benchmark datasets, these are just the models that the authors have picked to compare to. So we have to always look at this with some skepticism. Also, I just want to highlight the comparison of ISED results between the SegNeXt model and the aerial former model, which we talked about the other week. We see that SegNeXt is matching and mostly surpassing aerial former, a network that was specifically designed for semantic segmentation of remote sensing data. And not only that, but it's doing though with significantly fewer parameters, which is a really interesting result. And here are the results on other popular benchmark datasets. Again, there's only a handful of models here, so please take this with a grain of salt. So, has anything surpassed SegNeXt? It's been a year or so since its publication, so it's a natural question to ask. The answer is yes, the efficient VIT model from the MIT Han lab from April of this year. So looking at this table from the paper, we see that it not only performs better than SegNeXt in terms of performance metrics, but if you look at the mobile latency column, we see that it sees these significant to somewhat moderate speedups, but especially at the smaller efficient VIT size and the smaller SegFormer, smaller SegNeXt architectures, we're seeing a really significant speedup. Here's another figure from the efficient VIT paper that helps to visualize how it performed against SegNeXt and SegFormer. So this is the next architecture that's on my radar. The code and pre-trained weights have been released, so I've been working on adapting it into segmentation so that we can start using it in the lab. So that was my paper discussion on SegNeXt. Thanks for taking the time to listen, and please feel free to send me a message on the lab Slack if you have any questions or want to discuss the paper or any of the other papers mentioned here. Thank you so much.